Assalamu alaikum. In the last video, we talked about quantum harmonic oscillators. We discussed about the Hamiltonian, that is the factorizing the Hamiltonian of quantum harmonic oscillator. And then we have calculated the ground state wave function and the ground state energy. Today, we shall talk about the excited states of the quantum harmonic oscillator and the orthogonality of those states. So we started with the energy of simple harmonic oscillator, and then we constructed the Hamiltonian to be like this of the quantum harmonic oscillator. That is, the Hamiltonian has a kinetic energy term and a potential energy term. Just a correction, in the last video, actually the omega square, that is this square was missing, so it should be omega square. It was written as omega in all three cases. So the Hamiltonian, then we factorized, and we arrived at this equation here. N hat is the number operator, and A hat and A hat dagger are defined as these equations. Here we call the A hat to be the annihilation operator, and the A hat dagger to be the creation operator. This is also called lowering operator, and the A hat dagger is also called rising operator. So we assume that for any ground state, the annihilation operator when operates on the ground state wave function, it would annihilate the system. That is, it will give 0. So then for using this, we wrote the details of description of A hat. Then we came up with this equation, and then we solving this first order differential equation. We got the ground state wave function to be like this, and the ground state energy is half h cut omega. Now, so we showed that in the last video that when the number operator operates on the ground state wave function, it gives us 0. That is, the eigenvalue of the number operator when it operates to the ground state wave function is 0, because we can write this like n hat psi 0 to be 0 multiplied psi 0. So the eigenvalue of the number operator n is 0. Now, since we knew that the Hamiltonian is related to the number operator, and we said that then the eigenvalue of the Hamiltonian will be like this. Here n is the eigenvalue of the number operator, and E is the eigenvalue of the Hamiltonian operator. So this is because we see that they are linear, and whatever the eigenstate for the number operator would be the eigenstate of the Hamiltonian operator also. So now if since we got for the ground state wave function, we got the eigenvalue of the number operator is 0. If we put this in that equation, then we get the ground state wave function, ground state energy to be half h cut omega. Now we like to start from here. Now we like to see what the number operator gives when these operators on the first excited states. So to understand that, we need to know some of the relation between these operators, because we had lowering operator and rising operator and the number operator. Let's first calculate the commutator between the number operator and the lowering operator. So we know the number operator is A hat dagger A hat. So if we write it, and we just use the details or use the laws of commutator, so we can write like this way. Now we can see that A hat and A hat, they commute, so this should be 0. And we also know that the A hat dagger is 1. That is, we know that the commutator of dagger is equal to the 1. So this would be the -1. So therefore, from this commutator, we have minus A. Similarly, we have from this commutator is equals A hat dagger, because this is 0 and this is 1. Now we can continue like this, and if we calculate this one to be this one, that is n, the commutator of n hat and A hat square, then we arrive this, we have this, and if we calculate this one, we will have this one. So we can write a general expression for that. So since we see that when the power is 1 here, we have also the power 1 here, but we have also a minus sign. When the power is 2, we have 2, and we have a 2 factor multiplied, but the sign is again minus. Similarly, similar to this case with A hat dagger. So we can write the general formula for this commutator, that n hat, the commutator of n hat with A hat to the power k, that will give us minus k, A hat to the power k. And for the A hat dagger, it will be like this. We can also show that the commutator between A hat dagger and A hat to the power k to be like this, and for the A hat and A hat dagger to the power k is equals like this one. I leave this as a homework for the students. They need to do it to get used to with these kind of expressions. Just here we now again here we can, what we have used, just to give you a hint how we arrived is this, that when we know that the A hat when we know that when A hat operates on the ground state wave function, it gives us 0. So this is what we used here. Now, if we know that for an operator, if it operates on the 0, then the commutator, say let's say AB, this is equals A hat B hat minus B hat A hat. So if it operates on the wave function, then this operates on the wave function, then this will be A hat B hat psi minus B hat A hat psi. Now we know already from this A hat psi equals 0. So this gives 0. That means the total term is 0. That is, we are left only A hat B hat psi. So this is what we have used. So whenever we have two operators, the multiplication of two operators operates on the wave function in this order. A hat B hat operates on a wave function. But when A hat operates on the wave function, it gives 0. So this is equal to this one. Okay, so we need to remember these four actually expressions or commutators for further calculations. Now let's define the first excited state to be A hat dagger psi 0, because we know that when A hat operates on psi 0, it gives us 0. So we cannot build the second excited state or the third excited state with A hat dagger. So that's why we assume that the excited state can be built when the A hat dagger operates on the wave function, ground state wave function. So because we already have seen that this is the equation, and we know that when A hat dagger is equals to the 1. So when this operates on the psi, it gives us psi, but this is 1. So that's why. But using this one, we can also write, since A hat operates on the psi gives 0, we can write A hat dagger psi. So we can see that when A hat annihilates or gives 0 for the ground state, if we take this one to be the ground state, then this will be the case. That means this is not 0. This doesn't give 0. That is, when a hat operates on the wave function psi 0, it doesn't give 0, and it is no more the ground state, because if it was the ground state, then when a hat operates on that ground state, it should be 0. That means we have a hat dagger acting on psi 0 is not equal 0, is also not equal the wave function, ground state wave function, is something else. Let's assume this one to be the first excited state psi 1. This is what we wrote here, that psi 1, we define it to be the this wave when a hat dagger operates on the wave function. That is, when rising operator operates on the ground state wave function, we have the first excited state. So we are actually, this is our assumption, and we are going to show that this will be the energy eigenstate, and from that we will be able to calculate the energy eigenvalue. Let's move on. Now let's see what number operator gives when it operates on the assumed first excited state. So number operator, we know that we have just defined that psi 1 is equals a rising operator acting on psi 0. So we wrote like that one, and but this is when we know that when the number operator acts on psi 0, it gives 0. So what we have learned here, this one, we use that, and we ended up with psi 1. So it can also be written as 1 psi 1. That is, the eigenvalue for the number operator is 1 when it operates on the eigenstate psi 1. So so far what we arrived, that when the number operators acts on the psi 0, it gives us the eigenvalue 0. When it operates on psi 1, it gives us the eigenvalue 1. And when the rising operator acts on the ground state wave function, it increases the eigenvalue by 1 unit, because you can see this is psi 1. How we achieved psi 1? We achieved it acting rising operator on psi 0. So number operator for this wave function gives 0, for this wave function gives 1. That means the rising operator increases the eigenvalue for the number operator by 1 unit. And since this is what it does, this a hat dagger, when it operates on the wave function, it increases the eigenvalue of number operator by 1 unit. That's why it's called the rising operator. And since it was 0 for the wave function, for the ground state wave function, we may also call it the creation operator, because there was nothing, then it created a state. That's why the a hat dagger is called the creation operator or the rising operator. And in the same way, in the same way, a hat is called the lowering operator or annihilation operator, because when it operates on the wave function psi 0, it annihilates it. And we will also see that when it operates on a wave function that is not ground state, it decreases. A hat dagger increases, but the a hat decreases the eigenvalue for the number operator by 1 unit. Okay, so these are the conclusions that we have from so far. Now let's move on. Okay, let's see what this inner product gives. That is what is the wave function psi 1 is properly normalized or not. So we know that psi 1 we have arrived is defined as a hat acting on psi 0. So we wrote it in details. Now we can take this one in this side, but we need to take the conjugate of this, so it becomes a hat, because when we take the conjugate again, then this is the original operator a hat. Now we know this one can be written as the commutator, because we already used that if a hat psi 0 is equals 0, then we can write a hat comma a hat dagger psi 0 is equal to a hat dagger psi 0. You can see how important this equation is. We are using it again and again. So I suggest that the students should get used to with this kind of equation, and it can only be done by practicing again and again. So we write like this, but this is 1. The commutator relation of this is 1. So we have this, and we know that the ground state wave function was properly normalized. So we have finally get 1. That is the first excited state wave function is also properly normalized. Okay. Now, so we also knew from the last slide that when n hat operates on the wave function, first order state wave function, it gives the eigenvalue to be 1. So we can also calculate the first energy of the first excited state from this equation. This is what we use: h cut omega n plus half. So it gives us 3/2 h cut omega. Now, so we know we got the first excited state wave function and the energy for the first excited state, and we can calculate, since we know the psi 0, we can calculate this using creation operator on it as we defined it. So we just need to do the operation here, and if you remember that a hat consists of x and p hat. So when the a hat operator acts on the psi 0 wave function, you can get the psi 1. I suggest the student do this at home, so to get the explicit expression for psi 1, not involving a hat dagger or any other this kind of operators. Okay, now let's try what would be the second excited state. So we can define the second excited state in a similar fashion. So this is what we did, because we had first excited state was a hat dagger operating on the ground state wave function. So again, a hat dagger acting on the first excited state would give us second excited state. Now, before saying it the second excited state, let's put a prime here, because we are not sure whether this psi 2 prime is properly normalized or not. So just to check for that, we put it here. If we get that the psi 2 prime is properly normalized, then we'll say it's psi 2. If we get that this is not properly normalized, then we will redefine it so that we get the normalized wave function. So we do the similar thing. That is that we operate number operator on psi 2, and just do the calculation. You will get 2 psi 2 prime. And if we so the number operator for the the eigenvalue when the number operator acts on the psi 2 prime, it gives us 2. That is the energy for the second excited state can be calculated from the previous equation that we did here. This equation becomes 5/2 h cut omega. Now let's see whether psi 2 is properly normalized or not. So we calculate the inner product of psi 2, and we see that the result is 2. I suggest for students to do this at home, just to give you how we did. So we put the definition of psi 2 prime here. So as you can see, what we have defined here. Now we take these two one by one. First we take this one. So this side, it becomes A. Here it says, and again, if we take the other one, it becomes A again. Now from here, for these three, these three, we can write it as a commutator of this one, and we know the expression, the result for the commutator of this one to be 2 A hat dagger This is what we know this to be 2 ahead dagger. I have shown it you previously, and we also shown the general formula. You need to do the calculation, and then we have this one. So this is nothing but uh, so from here, this is same as that what we did in for the first order excited state when we checking the normalization condition for the first order excited state wave function, and this becomes psi 0. So we left off with 2. So the inner product is 2. That is the psi 2 prime is not properly normalized. But from here we can define the normalized wave function to be psi 2 equals 1 over square root 2 psi 2 prime. That is, we define 1 over square root of 2 a head dagger psi 0. That is, a head dagger is operating twice on this. A head dagger is operating twice on psi 0. This is what I have written here. So this is what we have, the properly normalized second order excited state wave function. And for the third order excited state, it would be like this. So this is difficult to see here, but when you calculate the third order and the fourth order excited state wave function, sorry, the third excited state or the fourth excited state wave function, you will be able to see easily that is this is not 1, 2, this is actually 1 factorial, 2 factorial, and for the first, second, third order wave function, this is 3 factorial. So in this you can do in home. You can even calculate for psi 4. Just do this way that we do, and you will see this will become 1 by square root of 4 factorial a head dagger acting 4 times on psi 0. So if we generalize it, we have the nth excited state wave function, or the energy states for the n excited state. This is equal to like this. Here we have n factorial square root and the a head dagger operating on psi 0 n times. And now we have also shown here that for the eigenvalue for the number operator is 2 here. Sorry, is 2 here, and we can show for the third excited state that it will be 3. For the third excited state, the eigenvalue will be 3, and the fourth excited it will be 4. But we like to show that the general expression. So we like to show that the energy, eigenvalue when the number operator acts on psi n would be this n. So in that case, we can easily calculate the energy eigenvalue. So let's do that. Before we go here, just to show that how the wave functions look like. This is the first. This is the ground state. This is the first excited state, and this is the second excited state. Okay. So to do so, what we are saying, we operate the number operator on psi n. So we know that the psi n we define the psi n to be like this. So you operate number operator on this one. So we have this, the number operator acting on that. Now we can write the explicit details of the number operator. This is a head dagger a head, and then we continue this. But this is what we know. Then this is actually we know can be written as this one, and we know the result is a head dagger n minus 1. So and the n multiplied, but we have a head dagger 1 a head dagger here. We have n minus 1 here. So if we do the product, we simply get this one, and we simplify it. So we have this one, because you remember psi n we defined 1 over square root to the n factorial a head dagger and psi 0. So this is what psi n. So we see that when the number operator acts on the wave function psi n, it gives us n psi n. that is the eigenvalue for this wave function, for this number operator for the wave function psi n is n. Therefore, the energy eigenvalue or the energy would be like this. Okay, so we have calculated, we have learned how to calculate the excited state wave functions psi n from the ground state wave functions, and we know the explicit expression for the ground state wave function. So we can calculate all the states explicitly using this equation, using this definition. And we also know that when the number operator acts on the wave function psi n, it gives the eigenvalue n. So we can calculate the energy eigenvalue immediately, and that is half h squared omega n plus half. Now you can see that n can be 0, 1, 2, 3, 4, etc. integers. Therefore, it has no negative energy, and the energy is also quantized. So this is also important. For the simple harmonic oscillator, for the classical harmonic oscillator, the energy can have any values, but for the quantum harmonic oscillator, the energy is also quantized. It can be half h squared omega, or 3 by 2 h squared omega, or 5 by 2 h squared omega, or it can continue like this, but it cannot have any value in between these two or these two. So the energy of the quantum harmonic oscillator is quantized. That's all for today. Thank you.